In this video, I'm going to walk you through the steps that you need to go through to analyze your data from the Enzyme Activity Lab and build your Michaelis Menten curve so that you can come to some conclusions regarding the effect of your mutation on the activity of this enzyme bagel B. So the very first thing that you're going to need to do is determine the concentration of bagel B enzyme, either wild type or mutant, that we added to the reaction. Because we're going to need to normalize by those concentrations, given that we're comparing two different enzymes here that were purified separately, separate preparations. They have different concentrations, and so to account for the fact that we have different amounts of enzyme in these reactions, we need to, once we get the reaction rates, divide by the concentration of enzyme. Right, so that we can compare apples to apples here. So when you open up your data sheet that you download from Canvas, you'll see that up here at the top you have your absorbance readings at 280, right? That's the wavelength that we measure absorbance for to determine our protein concentration. So in this case, for the wild type, the absorbance reading was 0.8, and for the mutant, it was 0.77. Now remember that in the Enzyme Activity Lab that we did, you diluted your proteins by either a factor of 100 or a factor of 10. In this case, both the wild type and mutant were diluted by a factor of 100. So we're going to use Beer's law to convert our absorbance to units of concentration in units to protein concentration in units of molarity. So we're going to need to use the molar absorptivity of beta-glucosidase B, which you have in your lab handout in the instructions for the data analysis section. It is 113,330 inverse molarity inverse centimeters, and the path length for this absorbance reading in that cuvette was 1 centimeter. So we know that absorbance is equal to concentration times molar absorptivity times the path length. So we rearrange that equation, and concentration is going to be equal to absorbance divided by molar absorptivity times the path length. So we can have Excel do this calculation for us. We click on the cell that we want the answer to appear in, type an equal sign, click on the absorbance. So we're going to divide that absorbance by the molar absorptivity of the bagel B enzyme times the path length, which in this case is 1 centimeter. Click enter, and there's our enzyme concentration. Now this is the concentration of the initial purified enzyme, but remember that we're going to have to account for that dilution that we did. So we're going to have to divide this concentration by the 100, which is our dilution factor. So again, we can have Excel do this calculation. We want to tell Excel to do this by typing an equal sign. Then this concentration over here divided by 100. Now, a nice thing about Excel is that since our data are arranged in this specific manner, and I've also put my mutant down below my wild type here, I can just grab this little green square in the bottom right hand corner and pull that down, and Excel will repeat that very same calculation using this absorbance reading. So if I click on this cell and come up to my formula bar, I can verify that that's the case. So it's dividing E6, so this is column E, this is row 6, so this value is being divided by the molar absorptivity times the path length, right? So these are my final enzyme concentrations that I used in the enzyme assay. So I'm going to need those numbers at the end, right before I'm ready to build my Michaelis Menten curve. So we'll put that on the back burner for the moment. We'll come back to that. So this is enzyme concentration in units of molarity after dilution. Okay, now I'm ready to move on and convert my reaction rates, which are these values that we obtained from the plate reader, from the units that they're currently in, which is absorbance per minute, to something that more closely reflects the reaction that's taking place here, the concentration of P&P product produced per minute. So the only data that I need are the data that correspond to the wild type that my mutant was run on, so whatever wild type was on that plate, and then my mutant values. I don't need any of this other stuff. So I'm going to copy this to a new sheet so that I have a little bit of a cleaner workspace here. You see those number signs down in the bottom just telling us those columns are not quite wide enough for us to see the data there. So I'm going to separate these out just a little bit so that I don't confuse my mutant with my wild type data. So my wild type data set is on the left, my mutant data set is on the right. I'm going to make those on the right. I'm going to make those a little bit wider. so that I can see those last values in row H. Now, before I get started in this, I want to do a little bit of data cleanup because you can see that I have some negative values here for that last row, which corresponds to row H, where there was no substrate added. So these aren't real reaction rates. This is just background noise from the machine. So anywhere I see a negative value, I want to change those to 0 because that's not a real rate. Negative rates are not possible for this reaction. All right. So having done that, now I'm ready to move on and convert these reaction rates from the units they currently are in, which is absorbance per minute, to units of molarity of PNP product produced per minute using Beer's law. So I'm just going to type that in here so I don't get confused later on by what I did with this data. So convert reaction rates from absorbance per minute to molarity of PNP product produced per minute using Beer's law. Now, once again, I'm going to have Excel do this calculation for me. I'm going to give it all of the numbers it needs to do that. I click on the cell where I want the answer to appear, type an equal sign, click on the absorbance. So the concentration is going to equal this absorbance per minute rate divided by the molar absorptivity of PNP, which is 10,660 inverse molarity inverse centimeters. Type that number in. And then actually I want to keep I want to put parentheses around this to make sure that Excel does this the way that I want it to do it, which is dividing by these two values, 10,660, and then multiplied by the path length. And now the path length for our 96 well plates is not 1 centimeter. It's 0.572 centimeters. So that's our path length that we need to type in here. So here's our Beer's law conversion, absorbance divided by the molar absorptivity times the path length. We click enter. Here's our new rate, now converted from absorbance per minute to molarity of PNP per minute. I can repeat that same calculation by grabbing this little green square in the bottom right hand corner of the cell, click and drag to the next 7 rows. And Excel has now repeated that same calculation with the other cells that are below that first cell that I type that formula in for. Likewise, I can click and drag to select this whole column, grab that little green square and drag it over to repeat that same calculation for the other 2 columns of data representing our replicate data sets. Right now, you might want to click in here and just verify that the correct cell up here is being used in that conversion. So this is the third data point down. So this should be using the third absorbance per minute reaction rate up here, which would be cell B5. And we can see that that is exactly what Excel is using to do this calculation. Likewise, we click over here. This is the third from the bottom in our third replicate, so that should be in this column C, and it should be row 8, and we can verify that indeed Excel has done that calculation with the correct absorbance per minute reaction rate. Now my mutant values are going to be basically put into exactly the same equation, and so I can just click and drag to copy all of these formulas over here below my mutants, and since I have exactly the same number of data points and they are arranged in exactly the same way, Excel will just redo that calculation with those numbers. And again, you can click through here and just verify that it's using the right numbers, and it is. All right, so we have now converted reaction rates from absorbance per minute to molarity of PNP per minute. But we're not quite done and not quite ready to average these values yet, because what we need to do now is divide by the concentration of Bagel B enzyme that we added to this reaction, right? So those concentrations that we determined on the prior sheet, the diluted concentrations, those are what we're going to need to divide by. So I'm going to copy these data over to that second sheet so I have them handy. And I'm going to do a paste special here and just take the values so that no formulas are being brought over that might confuse things. So I only want my final concentrations after dilution, so I got rid of those initial concentrations. So my wild type reaction rates are all going to be divided by this concentration of my wild type Bagel B enzyme. Likewise, my mutant reaction rates are all going to be divided by this mutant enzyme concentration. So once again, I'm going to have Excel do this calculation for me. I'm not going to do it by hand. Click on the cell you want the answer to appear in, type an equal sign, and then I want Excel to take this number and divide it by this number. Now, there are a couple of ways that you can do this. You can either just type this number in manually, because all of these are going to be divided by that number, or you can tell Excel, I want you to use the value in this cell for the divisor for all of these calculations that you're about to do, by using the $ to lock in row or column B and row 24. So $B, $24, and now Excel knows, okay, whatever number in here, that is what I'm dividing this cell by. So click enter. And here is my reaction rate now normalized to the enzyme concentration of the wild type. So once again, I can click and drag down the next 7 rows, repeat that calculation for the remaining data, and you can click through here and just make sure that that value is, the calculation is exactly what you expect it to be. So for this data point, we're expecting it to have used cell A18, right? Column A, row 18, and that's exactly what it used. And it divided it by that value in column B, row 24. So exactly as we expected. So we can click and drag once again and copy, click and drag once again, grab that little green square, copy it over. And so now this calculation has been repeated for these 2 columns of data, dividing by this enzyme concentration. Right? Now in this case, we can't copy and paste our formula over here because our mutant enzyme has a different concentration. So we need to divide all of these reaction rates by this mutant enzyme concentration. So we're going to type this in again, equals this reaction rate divided by, and again, I'm going to lock that cell, column H, row 24, and that's locked in that value. So Excel is going to use that same number for all of these calculations that it's going to do, right? So again, we can click through here and just verify G19, yep. And it used H24, yep. So everything looks correct there. Click and drag to copy that formula over the other 2 columns of replicate data, and we are done. We now have our reaction rates converted to what they need to be. We started in absorbance units per minute. We used Beer's law and converted those reaction rates to molarity of our PNP product produced per minute. And then we divided by the bagel B enzyme concentration that gave us those rates to adjust for the fact that these 2 proteins that we tested, the wild type and the mutant, had different concentrations. So we need to normalize for that. So we're ready now to go ahead and average these replicate data points and start creating our Michaelis Menten graph. Okay, so now I'm ready to average my reaction rates for my triplicate data points. So remember that we carried out our enzyme reaction at decreasing substrate concentrations as we went down. So if we go back to this that shows all of the values obtained in our 96 well plate, remember that we had rows A through H and then columns 1 through 12. What differed between row A, B, C, D, all the way down to H is the substrate concentration that we provided to the enzyme. In row H, we provided 0 millimolar substrate, no substrate was provided, right? And we get reaction rates of 0 as a result. And then row A had our highest concentration of substrate. So remember that those data going down each column are the reaction rates at decreasing substrate concentrations. The columns are exact replicates. So those are replicate data sets, and we're going to average across those replicates. So that's where we are now. We're going to determine the average. So this is going to be the wild type average. And I'm going to have Excel do this calculation for me. So this is going to be, I'm going to use a formula that Excel already has. It knows how to calculate an average. I just have to tell it that's what I want it to do. So again, click on the cell that you want the answer to appear in, type an equal sign, and we tell Excel we want it to calculate an average by typing average, and you'll see that function pop up here. You can either double click on that and you'll get an open parentheses, or just type an open parentheses. And now what you need to do is click and drag to select the 3 replicate data points that you want Excel to determine the average of. Hit enter, and there's your average of the 3 values that were tested that reflect the reaction rates for the test at the highest substrate concentration. We also want to determine the standard deviation, so how much these data points vary around that average or mean. So we're going to determine the standard deviation of the mean. So make sure that's wild type, standard deviation, so I don't forget what's in this column. Again, I'm going to use a formula that Excel already has built in, so I type an equal sign and STDEV. Now we're using sample standard deviation, so we want to click on this STDEV.S, open parentheses, and then select exactly the same 3 data points that you just averaged. Don't select the average itself, just the data that you used to determine that average. Hit enter, and now this is our average reaction rate and the standard deviation of the data around that average. We can click and drag to select those 2 calculations that were just done, grab that green box, pull it down, and repeat that calculation for the rest of our data. Now we're going to do exactly the same thing for these data over here, determine the average and determine the standard deviation. So I'm going to type my column headings over here. So this is going to be my mutant, average, and then in the next column is going to be my mutant, standard deviation. And I can click and drag to copy. What's being copied is the formula in each cell. Copy and paste those formulas over here, and Excel repeats the calculation, but using these data instead of the wild type. All right, so now we have all of the information that we need. We previously determined, we went through this in class, previously determined the substrate concentrations for row A through H, the final substrate concentrations. So I'm going to go ahead and copy those and pull them into this data sheet as an important bit of information. These are going to be our x-axis values, right? These are our x-axis values. We don't need that many decimal points. I'm going to format these as a number and go down to 2 decimal places. That's a little more reasonable. All right, so now I'm going to copy my averages and my standard deviations so that they're down here next to my substrate values, which are going to be my x-axis values. Remember that the data points are actually going to be the reaction rates. The standard deviations are going to be represented by the error bars that we then put on those data. All right, so I'm going to copy both my wild type and my mutant and then paste them down here next to my substrate concentrations. Now again, I need to do paste special because I don't want the formulas, I just want the numbers, the values themselves. I'm going to also copy my standard deviations. This is totally optional. You don't have to move your data around like this. This is just habit. It's the way that I've always done things when I'm plotting data. I arrange the data how I want it to be so that it ends up in the graph exactly as I expect it to be. So these values are my substrate concentrations. Those are my x-axis values in my Michaelis-Menten graph. These averaged reaction rates for my wild type and my mutants are going to be my y-axis values. By default, Excel will put whatever, when you create an XY scatter plot, Excel will put whatever data is in the first column as your x-axis values, right? So if I select all of this, including my headers, Excel will label my data series with the appropriate header, wild type or mutant. So I'm going to go up here to insert, find my scatter plot, select that first scatter plot, and here is my graph. You can see that my data series has been labeled. The red is my mutant, the blue is my wild type, and here's what that looks like. Textbook Michaelis-Menten graphs. Pretty amazing. We're not done because we need to add these standard deviation values onto each of these data points because each data point is an averaged reaction rate. So we need to add on those standard deviation error bars so that anyone looking at this figure is going to get information about how variable the data were around that mean. So if we click on the chart, we should get this little plus sign in the upper right hand corner to add a chart element. We're going to click on that, go down here to error bars, and if you click this arrow next to error bars, it'll pull up these options. Don't be fooled. Do not select standard deviation. Select more options because we want to add custom error bars here. So it'll ask you which data series you want to add your error bars to. I'm going to do wild type first. And over here I have my format error bars menu. So I want to come down here. So make sure that you're on the graph icon, that menu, and then scroll down until you see this custom option and then specify value. Because what we're doing here is we're telling Excel what the value of each error bar is, which we've already calculated. So again, I'm doing my wild type series, so I'm going to click and drag to select my wild type values for my positive error value, which is the up error bar. And then I'm going to click that little icon, select exactly the same data for my negative error value, which is the down error bar on the data point, and say OK. And now it has added those error bars onto my graph. Now Excel will add these little horizontal error bars which don't represent anything because we don't have any variance in our x-axis values. Those are our concentrations. There is no average there. So if you just click on those and hit the delete key on your keyboard, it will erase those and get rid of them. All right, so I've got my wild type error bars added on. Now I want to add my mutant error bars. So again, I come up here to the plus sign, go down here to error bars, click the little arrow. Don't be fooled by that standard deviation option. Click more options. And now I want to select the mutant data and make sure I'm on this little graph menu. Come down here to custom, specify value, and select my mutant standard deviation values as the values that my error bars are going to represent. Click OK. And now my mutant error bars have been added. Again, those little horizontal error bars, we can just select and then hit delete. And we are finished graphing the data, right? So we have our wild type Michaelis-Menten curve. We have our mutant Michaelis-Menten curve. And now by visual inspection, we can estimate where we feel like that data is plateauing. What does it look like? It kind of looks like it's, trending towards a plateau here. We can see that. Estimate that Vmax value, which is where we estimate that plateau to be. Find that 1/2 of Vmax, y-axis value, and if we imagine a smooth curve connecting our data points, find the intersection point for our substrate concentration, which is our x-axis value, to determine that Michaelis constant, right? And then interpret those appropriately. Now, we're not done here. If we're trying to create a correctly formatted figure, remember that chart titles are not used. Instead, we use a figure legend, which contains a figure number, and we can easily add that in Excel by making some space here by clicking on the white space of our plot area and then dragging up to give us a little bit of room down here. Going up here to insert and text box. Can add a little text box down here. This would be figure 2. And then description of the data shown in the graph as appropriate. And what else do we need in our, what else do we need in our graph to be correctly formatted? We need to add our axis labels with units. So you can again come up here to this little plus, add chart elements, click on axis titles, and now you have axis titles that you can edit. So double clicking on that will let you edit that. So these are, let me select, average reaction rates, and the units on that are going to be molarity of PNP per minute per molarity of enzyme, right? Likewise down here, this is going to be my substrate concentration. So substrate, PNPG concentration, and the units on that our millimolarity, and now we're done.